Hello everyone. You requested more videos on some of these slides, so we're gonna do that. Let me know if this kind of stuff is useful. So center of mass is something we'll be going over very soon, or well, we'll be doing in lab very soon. So the center of mass is by definition the point at which an unconstrained object will rotate about. The center of mass will remain motionless while the object rotates around it. You can think of in space as a good way to think about it. Objects rotating in space just keep rotating, and they rotate about the center of mass. Get to some of that. To find the center of mass, you want to sum up as many points as you can, and find the average both from their x position. So you sum up their mass times their x position. So if we break down a particle into this series of distinct points, then we take the mass of each point and the position of each point, and we add them all together in the x and y coordinates. In fact, I might pull up a little example. I didn't realize that actually the example is next in the slide. So, a common problem and a common assumption, I don't know, probably depends on how precise you have to be if it's engineering, but is two masses connected by a massless barbell in this case. Could be a string. Anyway, so it's a little simpler than having to do a collection of points. Instead, we're just going to take the mass 1 times the x1 position, and that's 0 meters, which feels weird. We've set our origin at this side of the barbell, and then the mass 2 times 0.5 meters, the length of their barbell. So it feels weird to me that this term is going to be 0. It feels like we're not counting this mass. So mass 1 times x1 times mass 2 times x2. Convert your units. 500 grams to 2 kilograms. But even though this term zeroes out in the second part, which I kind of didn't say, but it's on the page where you have in the denominator the combined mass of the objects, we've account for this mass, and so we are going to get the correct answer. And in this case, it's kind of intuitive. This thing is 1/5. Hold on, let me check myself. So I was about to say it's intuitive that it would be, so we find the center of mass to be 0.1 meters. And I was going to say it's intuitive that it's 20% of the way from the 2 kilogram ball to the 0.5 kilogram ball, because this is, and then I paused, like, because the 0.5 kilogram ball is 1/4, 25% the mass of this ball. So it's not actually as intuitive. So to explain why not make an exercise of it? I don't know that it's going to wind up being intuitive, but I can at least explain why. So say we weren't given masses, or say we were just given a relationship that M2 is equal to 1/4 M1. Then we set up our equation, and we also aren't given the length. So we'll say x of center of mass is equal to, and we'll still put mass 1 on at the origin. So mass 1 times 0 meters, if we prefer, or we should do. Then we have mass 1 times 0 meters. Then we have plus, well, instead of M2, we're going to write what we know M2 to be. We're going to substitute in 1/4 M1, and we're going to put x2. Yep, just for the position of x2. Don't even need to know what it is. We're just looking for a ratio, and then m1 plus, and once again, instead of m2, we're going to write down 1/4 m1. So then we simplify. Alright, so simplifying 0, that becomes 0, get rid of it. And then on the bottom, we're going to have, or on the top, we'll have still just 1/4 m1 x2. On the bottom, we will have 5/4 m1. We cancel our 4s, so you should see that. And we cancel our m1s. And then we have, oh, I'm a little off the screen. Yeah, cancel our m1s, cancel our 4s, and then we should have our answer that the x of the center of mass is equal to x2 over 5. So 20% or 1/5 of the way distance to the other connected object based on the fact that we have 1/4 of the mass. So there's not much intuitive to remember there. You probably, I mean, it's always safe to do the math. You can kind of look, we added 1 mass to the extra, to the 1/4 mass, and that's kind of what gave us this 5/4 ratio. Don't know if that helped it being intuitive at all, but was a good exploration. So let's get back to center mass stuff. We'll go over rotations in a bit more. So yeah, we'll worry about rotations later, or in a different video. So, and you may note this process of adding things together and over a series of space, that sounds an awful lot like an integral, where we would break down an object into slices and integrate over that. So like finding, well, in a weird way, finding the volume of an object. Hold on. Alright, this isn't real math, but in the way that if we were dealing with an object and we wanted to find its length in a weird, or its volume in a weird way, we could, along the object, it's a rectangle, so there's easier ways, but if we wanted to, we could, to find its volume, we could integrate each little segment of DL along its length, and multiply by the height, or perhaps so we'd integrate the height of each relative position, and if we had a variable height, then that would be the reason to do that. This is a rectangle, we don't. But anyway, it's the same. So there's better examples I'm sure you can find online, but just I'll share. So in looking for some property of a length like this, we can get that property by dividing it up into a bunch of tiny segments and integrating over function for each segment. So if we want the area, we integrate the height times each individual segment of length. That's a weird way to do it because it's a rectangle, but if we had some funky object with a variable height, then that would be a valid way to do it. So we're doing the same thing. We're integrating each x position of each tiny little segment of mass, once you're dealing with a contiguous object, to find the center of mass. So here's kind of what I was doing, but with mass. So integrating each little segment of dx, making it dm. So let's see. So we have a 1.6 meter long rod that rotates around its center of mass, and we have to find said center of mass. So if we're told it's uniform, the mass, the dm value over m has to be, hold on, let me get my head on straight. I think I got my head on straight. By the way, when I say hold on, that just means I'm pausing my recording, so you guys don't really need to hold on, but it's a reflex. Anyway, we should see we're squaring out a little section dx of this length of this rod, and that's supposed to have dm. And we should, so therefore, the dm should be the same portion of the total mass as the dx is of the total length. Or I think it's even intuitive to jump to this step where this section of mass is equal to the mass over the length times this segment of thing. It's density. I think that's what it. Well, density in terms of length. Anyway, and once again, I haven't put together the rotation video yet, so we'll be ignoring that. So then, center of mass, 1 over mass times, using the formula, and then we've come up with this definition for integral dm, where we've replaced the integral for dm with mass over length integral of dx. Let's see. So yeah, so now we're integrating x, and then it's calculus, so x becomes x squared over 2, the mass at big m's cancel, we still are left with the 1 over L, and we're integrating from the length to 0, which we defined as the starting point, the one end of the rod, to the other, and we get L squared over 2, and we finally get 1/2 length. And that's, so we took the long way around for a very intuitive answer, that for a uniform rod, the center is the center of the rod is also the center of mass. Alright, and here's something that caught me off guard when I was going through the slides, so it's worth explaining. So we're asked, we cut it in half at the center of mass, and we're asked which is heavier. And intuitively you might think center of mass must cut the mass in half, but remember that's not the definition. The definition of center of mass is the area that we rotate about in space, and it depends not just on the mass on each side. It depends a lot on the length, the distance from the side. We think we can offset a lot more when we get to levers. You can offset a lot more by being a lot further away. Is kind of the same idea. So we cut it in half. Then the hitting end is going to be heavier, basically because it's shorter. So basically the mass is more densely packed over here. And we could think basically the x delta, I've just put the image somewhere where I can actually draw on it. So if we put it'll be intuitive more if we set the center of mass, or we set the origin as the center of mass. We can see then if we have the same chunk of mass on two sides, shouldn't have really called it dm, well, that'll work, then this one on the left is like more valuable, you could say, than so we'll call that length 1 on the other side. And we're adding when we are calculating the center of mass, because this length 2 is less than this length 1. So that's an unintuitive bit, but kind of you can work it into what we're going to be doing with torque and such. Alright, let me know what you think of this video.